Hello everyone, welcome to lecture 23. Today we will continue the discussion on geophysical parameters of snow. In the previous lecture I gave you all the details why geophysical parameter is necessary to study, what is their role and why it is important, right. So today we will continue that and we will start with the snow depth. So snow depth refers to the vertical distance from the surface of the snowpack to the ground, right. So let us consider this is a ground, not the ice one. So in that case this will become the snow depth, right. So here you can see different example. So at different places different depth will be there, right. So at the higher altitude when we have steep topography, then the depth varies from the one location to another location. Snow depth is a critical parameter for understanding the extent and volume of snowpack, which plays a key role in hydrological studies. It is an essential indicator for assessing snow water equivalent. So this is very important. I hope you have understood the role of snow water equivalent. I have covered in the previous lecture also, and today also we will see more detail about the SWE. It provides valuable insight for water resource management, snow melt forecasting and various hydrological application. So once you know what is the depth of the snow, then you will be able to model how much amount of water will be released with changing temperature, right. So those kind of studies have been carried out. Under these circumstances, monitoring snow condition has proven to be especially useful using satellite remote sensing technique, because we all know that in situ measurements are very difficult in these terrain, because these terrains are rough terrains. The snow parameters have previously been retrieved by researchers employing a variety of optical and radar remote sensing data sets. Optical remote sensing, further it has a constraint because it cannot give you the data in the foggy condition, and the snow covered regions are mostly cloudy throughout the years. So in contrast, microwave remote sensing offers an advantage by acquiring images even under cloudy conditions. So these are the advantages of the remote sensing, why at all we have to look for an alternative source of information to estimate the geophysical parameter and particularly snow depth. So if you see the factors which are affecting snow depth are snowfall, temperature, then we have wind, then solar radiation, rainfall, this is liquid precipitation, then snow density and the topography. These all together define what will be the depth of the snow from the surface, right. So just to give you a background, the development of glaciers depends on the complex interaction of climatological, topographical and geographical factors, of which precipitation and temperature are the most important controlling climatic factors. For glacial development, high annual precipitation is required in the solid form. So that is why if you remember the positive mass balance, this will only happen when you have high annual precipitation. The proportion of precipitation received as snow, that is the ratio of snowfall received to total precipitation, right. So here the annual snow budget is greatly influenced by solar radiation, because the amount of energy which is falling on it, that defines whether it will remain on this particular surface or it will melt out. The geographical location also plays an important role, because the topography as well as the height from the MSL. So those things will define what will be the amount of solar radiation which will be received by this particular location. So here it defines the temperature of the region, distance to the ocean, influences the total or high amount of precipitation. Then comes the topography. You see here the main mass is somewhere here, right, it is flowing through this valley, right, but because of the topography it remains here. So, the topography has a very important role here in the snow accumulation. So, accumulation takes place throughout the winter. As we know, the solid precipitation happens only in the winter season, tailing off towards summer. Ablation is concentrated largely in the summer period, although the limited ablation may occur sporadically throughout the winter if temperature happens to rise above 0. So, here you can see the positive mass balance, right, when accumulation is greater than ablation. When we talk about this side where the negative mass balance, it is accumulation is less than the ablation. So, the balance year of a glacier, the positive winter balance and the negative summer balance are combined to produce the annual balance. So, if you see here this particular graph, so both remain same these points because the amount of accumulation and ablation, those are cancelling each other. So, because of that there will be no change or no net change in the snow accumulation in this particular area. So, if the area under both accumulation and ablation curve is equal, then the budget is balanced and the glacier is in equilibrium. So, there is no major change happening in this particular stock. If accumulation is in excess, then the glacier has a positive budget and it is growing. So, slowly it will start growing. If the budget is negative, then the glacier is shrinking. So, it will start shrinking and this mouth will be something like this, right. Accumulation is greater at higher altitudes where ablation processes are more limited due to lower temperature. Ablation dominates over accumulation in the lower part of the glacier. So, here the ablation will be more, right, in this region. The point at which ablation and accumulations are balanced is the equilibrium line. So, for this maybe you can say this is a equilibrium line, do not consider this. So, the factor affecting snow depth, I hope you have understood how the snowfall, temperature, wind, solar radiation, rainfall, snow density and topography will play a critical role here when we were talking about the snow depth. So, there are two types of measurement, one is manual, another one is automatic. So, when we say manual, we have a stake, right, this is a snow stake which has some numbers here, right. So, you can see, and every year we come and mark whether it has the positive or whether it is going down. So, then it will be negative budget, right. When we talk about this automatic measurement, so here the modern weather station frequently employs ultrasonic or laser sensor mounted above the snowpack. These sensors emit pulses and measure the time it takes to the echo to return from the snow surface from here, thus determining the distance to the snow. By knowing the sensor height, the snow depth can be calculated. It releases the pulses and then it measures the time, how much time it has taken to come to this particular sensor, and then it will be having the information about this height, and then it will calculate how much there is a change in the snow in this particular surface. So, for this we have done various field investigation. So, this is one example where we have reached to the Rathong glacier. So, it was a very difficult trek, 96 kilometer to and fro trekking was required, and here we have seen different topography which is available for this particular glacier, and we have also installed the snow stakes, right. So, this is my team, we went together and then we had the installation of this snow stakes. The SAR polarimetry, or we also call it polarimetric SAR, and the SAR interferometry, which is also known as interferometric SAR, have been proved to be helpful in estimating snow physical parameters such as snow depth, particularly snow density and snow water content, right. Time series Sentinel-1 datasets are used by various researchers to study the inconsistency of snow depth in the mountain of the northern hemisphere. The link between particle anisotropy, snow depth and copolar phase difference are also used to retrieve the snow depth and snow water equivalent. The copolar channels are typically provided by commercial polarimetric SAR data, which are expensive. So, in contrast, sensors like Sentinel-1, one copolar and one cross polar channel, which is VV and VH, are freely available. So, that is why we concentrated on this Sentinel-1, whether we can develop a method which can estimate the snow depth and other geophysical parameter, and this is freely available in the public domain. So, that is the advantage. So, when we talk about the microwave remote sensing, here you can see the example. So, how the different birds and the fishes, they are using the echolocation method to target their food, right. Similarly, we have satellites which are looking at the ground from different location, and this information we are using to derive the information about the target, right. So, I hope you remember the interferometric SAR configuration. So, here you have the first SAR satellite. So, here you have two satellites which are available at two different locations, and these locations are separated by the baseline, right. And here you have to see that this particular location or this particular area is being captured by both the satellite at the same time or at different time, right. So, these information can be used further to investigate and derive the meaningful information. So, difference between the two path lengths related to the difference in phase of the received electrical field. So, if you see here, because of this we have the phase difference, and these phase differences are further analyzed to extract the information. So, this is another example how we are measuring the images from the using the single pass and the repeat pass concept. So, here when we talk about the single pass, two radars acquire data from different position at the same time. So, this is called single pass. When we talk about the repeat pass, here again we have two radar, but they acquire the data from different position at different times. So, that is the difference, right. So, to understand surface dynamics, especially surface subsidence, interferometric method that make use of space-bound SAR have been thoroughly studied. Repeat pass interferometric dataset and approaches entrenches in INSAR have been extensively employed for the estimation of snow water equivalent and the analysis of snowpack dynamics. However, INSAR signals are mixed with the topographic phase. To solve this problem, the differential INSAR, the DINSAR technique is used. So, today I will tell you what it is and how we are doing this, right. So, the DINSAR method is considered more accurate than INSAR as it is capable of providing relative measures up to a few centimeter or less. So, the accuracy is very high for the differential interferometric SAR. The DINSAR path has been exploited to project the snow water equivalent for dry snow using interferometric phase information. C-band INSAR, we have Sentinel-1. Records from European remote sensing satellite are utilized. Subsequently, research utilizing Sentinel-1 dataset has focused on estimating snow depth through DINSAR method, right. So, the obtained snow depth indicate an enhancement in overall accuracy compared to conventional INSAR technique. So, today I will show you how our results are better than the earlier proposed model and how using this DINSAR helps us to identify the information. The snow depth inversion model is a function of the snow dielectric constant, radar wavelength and incident angle or the local incident angle, right. So, studies also indicated that the estimation of snow depth largely relies on the accuracy of two components, that is snow phase contribution and the snow dielectric constant. So, these two informations are used. So, these two components can be determined through in situ data or from other remote sensing data sources such as multispectral data or the full polarimetric SAR data. So, full polarimetric means you have VV, HH, VH, HV, all the combinations are available. Researchers have used a multispectral data based snow cover map threshold for snow phase correction, right. So, however, a snow mask derived from Landsat image is frequently used to extract the Sentinel-1 backscattering. So, study by Singh et al. 2025 employed Landsat 9 based snow cover product and snow geophysical parameter, which is wetness, density and dielectric for snow depth estimation. In our research, Sentinel-1 data along with supplementary data derived from in situ measurement and enhanced version of optical dataset such as Landsat 9 have been utilized to construct a model for snow depth inversion. So, a state of the art snow depth inversion model has been proposed by my group, integrating information from Landsat and Sentinel-1 data. So, here our study area was Arunachal Pradesh in India, which is from the eastern Himalayan region, right. So, here you can see the SAR data which is used to generate the digital elevation model. So, let us say this is time 1 T1 and this is T2 time. If there is a change in the height, that we will consider the snow accumulation, right. So, that is being used here for identifying the snow depth. This is further utilizing the other method. So, here you can see the study area and the locations are highlighted here where we have done the field investigation, right. And these some of the field photographs. So, this is the methodology which we have used. So, here this left hand side is the DIN-SAR processing which we have done in the SNAP. Similar step are followed for the VH channel. Right side we have overall methodology for snow depth inversion model. Similar steps are followed for the VH channel. So, this is for the VV, but we have also done the same processing for the VH channel, and then we have estimated the wetness, permittivity, and then subsequently we derived the snow depth. So, here you can see the snow depth inversion model which is developed by my group. So, it has the mean in situ snow depth which is 34.17 and the mean model snow depth that is 34.28 and the RMSE and MAE is given here. Whereas, the earlier methods you can see the values are in the similar range, but we have better accuracy, right. So, here you can see the values lower bound, upper bound, RMSE, R square, adjusted R square which is given here, right. So, this modified model incorporates snow permittivity for each pixel value obtained from Landsat 9 level 2 data set. We set the NDSI threshold for the snow cover map to be greater than 0, guided by our in situ measurement, because we have visited the field and then we have identified this should be the threshold. The degradation of NDSI value at the measured location is attributed to the presence of vegetation as evidenced by the field photograph from the study area. The average modeled snow depth at the measured location was determined to be 36.70 centimeter, whereas the expected snow depth observed in the field was 38.17. So, the improvement in RMSE and MAE for our proposed snow depth inversion model can be attributed to alteration in the scaling factor for each VV and VH, because we are talking about the Sentinel-1 data, and the weight function. Now, still there is a room for further enhancement of the efficiency for our model. which could be achieved through in situ analysis of snow physical variables like snow dielectric density and wetness, utilization of high resolution DM instead of SRTM 30 arc second, refinement of weight and scaling factor, and additional pre-processing improvement in DINSAR technique. So, these are the future scope of this work. So, if anybody is interested, they can go for this future research. Thank you. I will end the part 1 here and then we will continue this discussion in the part 2. Thank you very much.